I wanted to record this, hide the controls, make this big. So now we can start. I think that will be our last lecture, maybe even that will be shorter than usual lecture we will see. The topic is Stokes' theorem, and that is the Stokes' theorem in the most general form. So we have M manifold with boundary, which is a generalization of our previous manifold notion, manifold with boundary. And we call the boundary dm or bm. Maybe I convinced you that dm is, in the context of Stokes' theorem, better. So what does it mean, a manifold with boundary? We have two kind of charts. We have usual charts, which is some open set in our manifold, which is mapped into some domain in Rn. And we can actually always assume that this domain in Rm is a n-dimensional cube. So something like this, which is here the origin. This is one in one axis direction. This is one. So a cube of open cube. So an open cube with side length 1. We can always do that. Well, for instance, if we have a chart, we can always choose a point within, and well, somewhere this point is somewhere here, and then take the cube around that point, and then just take the pre-image of that. And since we can do that for every point, we get obviously a cover of our manifold, an open cover of our manifold, where the chart domain in Rn is just a very nice open cube. And we have boundary charts. Boundary charts, well, also some kind of which are mapped to also a cube, but including, well, say this this here, say this is xn is equal to 1. So maybe with a different color. So we have some part here, which goes here. Say still, well, we want this homeomorphism including that piece of the boundary. So and all points which map, which belong to a boundary chart and which map to the this piece of the boundary here, xn is equal to 1, this face of that n-dimensional cube, that of course becomes n-1 dimensional. We call these the boundary points. So these are the boundary points, and they form this what we call dm. So now actually in this way, these n-1 dimensional faces of the cubes become charts of some neighborhoods of boundary points within the boundary. And in this way, this boundary actually becomes itself an n-1 dimensional manifold. Well, in this case, of course, we need some kind of also smoothness. So n-1 dimensional topological manifold, but if you want this a smooth manifold, and I think we want that, then we can we also need here some this mapping to have derivatives if restricted to the boundary, and also we want this all these derivatives along the boundary. We want them to be continuously connect with inside. I don't want to go too much into details here. So we have these two connected manifolds with the boundary. And if our manifold is oriented, and here we want oriented, if M is oriented, well, probably we will assume that M as a manifold is connected. Then we can at some point Txm we can find in this vector space we can find an orientation just by choosing a basis. Maybe E1, well, for a basis it goes downstairs. E1 En is a positive basis. We can choose that. So we can choose a basis and declare this as a positive basis. But if we have chosen that, then in the whole neighborhood, we also have, well, kind of the same basis in the, so say d by dx1 and d by dxn, and here it should go on the top. In some coordinate chart, we have the bases in this order. They form a positive basis. With any permutation, with any even permutation, we preserve the basis, the orientation of the basis. With any odd orientation, we change it. And that is also when we make the coordinate change. These bases multiply with the Jacobi matrix, and the determinant of that will change the orientation or will keep the orientation. So we can extend this orientation in some open neighborhoods, and because of the connectedness, this orientation actually extends to the whole manifold. If we can do that. So it is uniquely determined, but manifolds may not be orientable. So you may know the famous Möbius strip, where you can start with in some point and come back to some point, and along this curve on open sets, you extend your orientation. You can do that along a curve, all with open neighborhoods. And when you come back to your point, your orientation may have changed. I don't know if I can create some Möbius strip. So if say you have a strip you twist it one time or half a time, depends on how you count. Glue it together. It is something like this. So you can imagine the story of a bug traveling on one side, and when it comes back after one round, it is on the other side, and if it goes one more round, it comes back to the original side. I think you all have seen the Möbius strip, which is not orientable. We cannot orient it. So there are manifolds. It is actually a perfectly nice manifold. We can cut it into pieces with some overlap, and it would be a perfect manifold with two charts. Even more interesting, there's is Klein's bottle, and is all kind of non-orientable manifolds, but we assume it's orientable, and if it is orientable and oriented, then the boundary also has an orientation. So if M is oriented, then this implies that the boundary also inherits an orientation. So we can always say well, if we have here a positive a basis where this En, which corresponds to this last coordinate here, this is at the last place, then the remaining vectors form a basis on each tangent space on this face of our this boundary face of our cube, and we declare this a positive basis. So if we have a positive basis inside, we can get a positive basis just by making the extra tangent vector this normal vector. This normal vector, we making this the last vector and then dropping that. So that is something what would work. Okay, so in the context of Stokes' theorem, we work with oriented manifolds, and the orientations compatible in this sense, and I probably have already written last time. So the integral over the boundary of a manifold of the exterior derivative of an n-1 form is an n-1 form. If we take this exterior derivative, then d phi is obviously an n form, and that is actually the same as the integral over M itself. No, what am I saying? Here we have phi, the n-1 form over the n-1 manifold. So we can always integrate an n form over an n manifold, an n-1 form over an n-1 manifold. So here we have d phi. So this is d phi is an n form. And these integrals are the same. And of course, you know some instances of that. We have first of all Green's theorem. The Green theorem, and in the context of Green theorem, you would also have discussed orientation. So we have a domain which is, say, oriented counterclockwise, and then the boundary is also counterclockwise, and we have then the double integral. So here we always just use the integral itself, no double or we wouldn't write here n integral signs to emphasize that we are actually talking about an n-fold integral. So it would be, we have talked about double and triple integrals in calculus and multivariable calculus. So here we actually have n-fold integrals and n-1-fold integrals, and we just write one integral. And if we indicate that the integration is over an n-dimensional manifold, then of course it's an n-fold integral. And the way we compute such integral, we also discussed last time. We would have our a partition of unity, and that actually takes, we have here this, I don't remember if how I, maybe chi j, and here, which is actually the whole sum is a constant 1, so multiplying this by a 1 doesn't change anything. Chi j, we can put in here and could put in here, and then everything will be restricted to a coordinate chart, and we can use our chart coordinate mapping to transfer the whole thing into our usual multivariable setup, where we form a usual, well, if you want, Riemannian integral. Everything is smooth here, and our charts actually are just boxes, so they are bounded, and we have smooth functions which at the boundary are 0. So actually everything is bounded, can be integrated, is no trouble at all. And also in these boundary charts, of course, our we actually need also to adapt our partition of unity, so that we have here some functions which have the following property. They are say one, including here part of including a part all inside here. So I was wrong with my picture. So they are one at the support actually here joins to the boundary. So there could be one at in some neighborhood of a boundary point, and then falling down to 0 in some other part, and are 0 outside here. So we want this kind of partition of unity mappings when it comes to boundary charts. All of this can be done. Actually, I Googled for a proof. If you want to do all details, that would be a bit lengthy. If you, I Googled for a proof, and what in particular came up are lecture notes by a colleague from the ANU, Ben Andrews, who's really great, probably one of the best Australian mathematicians at this time. And I really like his differential geometry course, which he gave at the ANU, and that the lecture notes are available online. So it comes in particular up if you ask for a proof of Stokes' theorem. It came up in my search. So okay, so we cut this in pieces, and that is actually also the key for proving that, because if we cut that into pieces, we have to prove the following on two types of charts. We can prove it at such a chart, which is an open cube. And for a form, well, a form, we have this form phi with the phi inside. And but if we multiply this with the partition of unity function, then this is all zero near the boundary. Near the boundary. Near the boundary, this is just identically zero. So it and of course also d is also of course near the boundary. So on the boundary, we don't have anything. So in this case, the integral of d j phi, no, not d, sorry, just this one, on the boundary is of course equal to zero, because the form is zero, so everything is zero, so no problem. So what we need to show is also that it is inside. So maybe I call to make it simple. Actually, what I did not exactly like in Ben Andrews' proof is his notation, because he really uses consequently notation of taking the form into the chart, so that he takes all the mappings with it. So the notations become very clunky. So let's say we are just have this psi which is zero near the boundary. So now what is the psi? Well, what is psi first of all? This is an n-1 form, and an n-1 form on an n-dimensional manifold consists of n terms, so it's an n-1 form on an n-dimensional manifold, M. So it is a sum of, say, some functions, say fj, and dx1, dx2 in local coordinates in our cube. So now until dxn, and then often people use that notation. So dxj is omitted. So making here that little omission sign, a little triangle with a j there, which says j is missing. So j is running from 1 to n. So that is actually what such an n-1 form is. Physicists might say it's a vector because it's n functions, but we know it isn't. It's not a vector. This is an n-1 form. And so how do we differentiate it? We know the rule of differentiation. Differentiation annihilates all these differentials, so we don't worry about the differentials. We only worry about the function in front, and the differentiation on the function in front gives us the differential of this function. So if we differentiate it, it gives us dfj by dx1, dx1 plus and so on, dfj dxn, dxn. This is the differential. And in this whole differential, there's only one term which is interesting for us. And this term is actually the df by dfj by dxj, which multiplies with dxj. The only differential which does not appear in that product of differentials, and the only one which would not make this product immediately zero. If we would have well, dx1 with that product which has already dx1 in it, it becomes immediately zero. So the only way it does not become zero is that. So actually we want we actually only have this. So it is sum j equals 1 to n. Now dfj by dxj, it is some kind of divergence what we compute here. So say dxj times dx1, and j is omitted here, dxn. I write it here in this wrong order in order to not bother with the sign change. So if I would put the dxj in its alphabetical, or what is it, or well, right place, then what happens? Then I have to multiply with -1 to the power j minus 1, because I would need to make a j minus 1 swappings to get it in the right place. So I'm not doing that. But if I would do that, everything would become a bit nicer, but with plus and minus stuff happening. So now I need to show that if I integrate this, so I have many such terms, have n such terms, but I look just at one term. So I have this integral over my cube. So let's think we are already in the chart of say such a term dfj, dxj, dxj, dx1 times dxn. So, and I said when I am on my cube and my frame, well, the coordinate system is positive oriented. If this is positive oriented, then it is just normal integration. It is normal n-fold integration, and n-fold integration can be performed as repeated integration, as we know from multivariable calculus. So I can actually do this integration with respect to xj first, and that goes from 0 to 1, multiplied by dfj dxj, and then I perform integration over this n-1 dimensional cube, which depends on just these. So this first, and then dx1 dxn without the j. And now all what remains is to apply the fundamental theorem of calculus. So in this, for this integral, the theorem of calculus, a fundamental theorem of calculus, says this is just fj evaluated at 1. So here we have x1 and here we have xn, but at the place j it is just 1. So this is how this repeated integration, we integrate with respect to the xj variable, and the other variables are just whatever they are, and minus fj of x1, 0, xn. But this is our function fj restricted to the upper phase. The phase xj is equal 1, is one phase. And on the phases, our form is equal to 0, which means all of our fj's are equal to 0. So here, this is, of course, 0. And this is also 0 on the lower phase, on the phase. Xj is 0. These are boundary phases. Boundary phases, and here is everything is 0. It's not so much different when we have a boundary chart. So basically, this shows us that for this integral, which we have here, this integral, where we integrate over the whole manifold a differential of an n-1 form, a very special n form, which is the complete differential of an n-1 form. If we do that, it turns out it only matters what is near to the boundary, because what is not near the boundary can be taken out. So maybe I give you a picture. So if we have a huge manifold with boundary, and we have some function which is 0 in 0 at most of the manifold, and just when we come close to the boundary, it becomes 1. So we multiply that. Then for the integration, only this part matters. This part here inside does not matter at all, because all of this, what is not close to the boundary, can be covered by charts which are not boundary charts, as everything which I can cover with charts which are not boundary charts does not contribute to the integral. So the integral is really, in this case, something which happens at the boundary. So now the boundary charts. The boundary charts. So what happens to the boundary charts? Well, pretty much everything the same. So we have only this for xj equals 1. We have here something. We don't have anything on these boundaries, and we don't have anything inside. So our integral actually becomes here this integral, the integral. No, what am I saying? The integral. Of this df j dxj xj dxj and so on, dx1 dxn. Here is no j. This actually now becomes also by repeated integration the integral from 0 to 1 of dfj dxj dxj. And this now, by the fundamental theorem of calculus, becomes actually f of x1, x2, 1, xn. So which is exactly, well, fj is exactly fj restricted to this boundary phase. And if I integrate this, then what I get is exactly the integral over the boundary, this upper boundary phase of fj dx1 dxn, which is here with j missing, which is exactly the part of the form which I have been considering here. So if I would consider another summand of this form, so different j for a different j, I would just need to choose here a different phase of the cube. So that works in all direction, and that is basically also a proof for Green's theorem. It's a proof for Gauss's theorem, and it is also a proof for the traditional Stokes theorem. So what do we have here? So Green. What is Green? We have a domain on the two-dimensional plane. We have a form f1 dx1 plus f2 dx2, and it claims with our orientation the integral, well, maybe the omega, let's call the domain omega, of f1 dx1 plus f2 dx2 is equal to the double integral inside of the exterior derivative, which is minus df1 by dx2. The minus comes before because I want to swap dx1 and dx2 plus df2 by dx1. But by the way, I was not very much detailed by figuring out how these orientations work. So if all the orientations are correctly taken into account, then this is what we get. Now the usual Green, is that the usual Green? Yes, this is how we usually formulate the usual Green theorem. Then the Gauss theorem or divergence theorem is an R3. And we also, well, but by the way, it also works for a domain which doesn't, I will get to this later, with a domain which is more complicated like this. But in this case, we get two parts of the boundary, and we have to integrate here over all parts of the boundary. And here, by the way, the outer normal. So if we look from inside the domain, the orientation is from inside moving left, and if we look to this inside boundary and we also wanted to go left, we have to orient it in this way. So the inner boundary goes in the other direction than the outer boundary, and if we do that also for this kind of domain, that works. So we do not make any assumptions on the topology of the domain, and the same with Gauss's theorem. So now, what is Gauss's theorem? We have a double integral on the boundary of, say, f, maybe I call it f1 dx2 dx3 plus f2 dx1 maybe dx3 plus f3 d1 wedge dx2. We may also sometimes people put dx3 in front of dx1, then that f2 is kind of the opposite sign. So this is now the same as the triple integral over the whole domain of well, the divergence, so to speak. So here, if we well, maybe we put a minus here. It doesn't really matter because I didn't say what f2 is. So let's choose f2 so that this has a minus. It just comes out nicer. So in this case, we have, of course, df1 by dx 1 dx1 wedge dx2 wedge dx3. And from the second, we get a dx2 here. If we swap it with the dx1, that would compensate this minus sign. So plus df2 dx2 plus finally df3 by dx3, so to speak. In physical terms, the divergence of a vector. In our terms, just the exterior differential formally applied to this general two form. It's a two form. It's R3, which has three components. So and now the traditional Stokes theorem is actually on a surface, curved surface. But a curved surface is a manifold, is a two-dimensional manifold, and the boundary is now a one-dimensional manifold. And if we apply our charts, this is actually nothing but going back into flat pieces of R2. This is actually nothing but Green's theorem. But that would be the most difficult to prove because we would need some parameterization of all of these curves, which makes it technically very difficult. But if we have the notion of a manifold and we can switch to charts, then that is just the same proof. So that is the usual Stokes theorem. Is actually nothing. It's the same as Green's theorem, just on the curved two-dimensional manifolds. So these are the known instances where we have that. And well, as you see, if we pass to charts, no matter boundary charts or inner charts, it just reduces to two theorems. One theorem is the theorem of reduction of n-fold integrals into repeated integrals, sometimes also called Fubini's theorem. And I think Ben Andrews also calls it Fubini's theorem, a great Italian mathematician. So Fubini's theorem, or just the theorem about reduction of multiple integrals to repeated integrals. So this is how we computed integrals in multivariable calculus. Instead of writing some kind of very complicated Riemann sums or so, we represented this as repeated integrals and applied our knowledge, in particular, the fundamental theorem of calculus from one-dimensional theory. Well, and the in essence, if we do not pay attention to all these charts and coordinate maps and changes of coordinates and all this kind of thing, then it is just, well, this Fubini theorem and the fundamental theorem of calculus and nothing else. So that is actually what it is. So you could also think of this if you have some integral and you have some function df, which you, well, df here, which you integrate from a to b, then it doesn't matter what this function does inside here. It does not matter at all. All what matters is f of b and f of a. So everything inside does not matter. So we can actually change this function inside as much as we want as f. So we can f change as much as we want, as long as we do not touch the continuous boundary values. Of course, it must be continuous here. And as long as we do not touch these continuous boundary values, we can change it inside as much as we want, and it will not affect the integral of the derivative of it. So there's one more thing which may also be relevant to physics. It is, well, topology, some topology. We may, well, so, in order to understand the topology of a manifold, we may want to triangulate it. So what well, triangulate means cutting into triangles. So what's a triangle? Well, we are interested in triangles which are called simplices. So one is a simplex, many are simplices. And well, a one-dimensional simplex is just a segment from 0 to 1. A two-dimensional simplex is a triangle which has a corner 1 here, 1 here, and 0 here. So that is a two-dimensional simplex. And a three-dimensional simplex is something like this. Pyramid, also with here the origin, here one in x direction, here one in y direction, and here one in z direction. So you see you can do that in all dimensions. So that is the very simple domain which you cut out by the positive, well, quadrant octant. I don't know how is this. Is this an entant? I don't know. So the positive, all this positive octant, and the plane which passes through all the ones on the axis. At each axis we have a 1, a positive 1, and through all these points we have an n-1 dimensional plane, and that is the remaining phase to cut that off. So all these simplices, they have some interior. So we have some interior and we have some boundary. And by the way, we want these simplices, we want to be them also oriented. So here we have maybe the usual orientation from left to right, from 0 to 1, from smaller to bigger. And then we get the right bound positive and the left bound negative. So here actually the boundary consists of two pieces. A plus and a minus. So we can here have the boundary operator in topology. So we can to this thing we apply the boundary operator. So I also and this is these 2 points. And this is oriented, and this is also oriented. And now we can have here also a boundary operator. If we have this a triangle, then apply the boundary operator. Then this is oriented like this. Then we have this piece, and then we have this piece, and then we have this piece. So actually 3 pieces of boundary, and these boundaries so what did I? Yeah. Well, and say we go this way. This is plus minus plus minus plus minus. So this is the same point which one comes with a plus and a minus, and this is the same point which comes with the plus and the minus, and here the same point which comes with the plus and the minus. So if we actually add them together, this has no boundary anymore. This has no boundary anymore because the boundary points of these 3 simplices, which are the boundaries of our triangle, they come all with they cancel each other out, and we can actually do the same here with our pyramid. We have triangles as boundary, 4 triangles which form the boundary, but also 2 of each of these triangles, they have a common edge, and at this common edge they have opposite orientation. So if we have these 4 triangles here and add them together, or the boundaries of these triangles, if we add them together, then they also cancel out. So the boundary of a boundary is always 0, which may ring some bells when we differentiated forms and we applied the differential. Why have I done? There's nothing like this here. So when we applied the exterior differential on a form 2 times, then we also got 0. We always got 0. So we had then the notion of an exact form and a closed form. Yeah, and just a form. So, but when we differentiated the form, the degree of the form went up. Here, when we apply the boundary operator and we use the round D, but also a D like differentiation, it is in a way similar, but the dimension goes down. So if we apply find the boundary of some n-dimensional object, the boundary will be an n-1 dimensional object, and that already would not have a boundary. So now we can formally add, as we basically have done here, one can formally add simplices. We can find formal combinations of them. we can scale them with positive integers. So just taking two copies of the same simplex. We can also scale them by negative integers. Negative integer means we change the orientation. And if we really want, we can also take rational or even real or complex combinations. And whenever we do arithmetic with it, well, just using this as a vector space, where the simplices are a basis element, so we can scale them. Formally, it does not make much sense unless you want to interpret this as some kind of area or so oriented area. If you can do that, so then even that makes sense. Okay, so we have these simplices and we have the boundary operator on simplices. So how does that come? Well, maybe before I come to manifolds, we can have a combination. So say Cn is some n-dimensional simplex, and we can have many of them, and then the sum of them, say alpha j Cjn, something like this, is called a chain. So a chain of simplices. So that's called a chain. I have introduced the boundary operator. So if the boundary operator applied on some chain is equal to 0, we actually call this chain a cycle. A chain is a cycle. So cycle is something which goes round with no end. So no boundary, no end. This is where this terminology comes from. So a cycle is a chain with no end, with no boundary. And then we have also such chains which are a boundary of something. And these, in this case, C is called a boundary. So we have chains, and within the chains we have some very special chains, which are cycles, and within the cycles we have even more special chains, which are boundaries, and I give you an example. Say if we have on a manifold, we have something like that. So this is nothing. It's just these three one-dimensional things. But our manifold has here a hole. So manifold is something like this, and we have these three things. We have a cycle. This is a cycle. But it is not a boundary because it does not bound triangle on my manifold, because the triangle which it bounds has a hole. So it's not a triangle. This is a cycle, but not a boundary. So now, well, coming to many, before I give you more examples of cycles which are not boundaries, if we live on a manifold, everything is curved, and we would say here a simplex on the manifold M is something which can be mapped into a normal simplex. So something which under diffeomorphisms is actually a simplex. So a chart which looks like a simplex, and what I used here were actually also simplices, because cubes and pyramids is topologically is the same thing. Is the same thing. So we can also have this on a manifold, and we can now triangulate a manifold. Triangulation means to represent our manifold as the sum of such simplices. And these are n-dimensional simplices. So let's think of finitely many of them. So for instance, if we have, well, such a thing is just the same, topologically can be stretched into something like this. If we have here a hole, so what can we do? We can have a triangle like this, then we can have a triangle like this, and a triangle like this, and a triangle like this, and maybe now a triangle like this. All of these are triangles. And yeah, all of these are triangles. So that would be a triangulation of that disk with the hole, or that domain with the hole. So it still can be triangulated. And here we could have, as I showed before, we could have something like this, which is a cycle, but it is not a boundary. Now there are more. This is all two-dimensional. Another two-dimensional is a torus, a donut. So we are interested here not in the solid part of the donut, but we think of the donut just as its surface, the two-dimensional surface. And then we have some cycles which go this way around the donut. And this is a cycle, but not a boundary, because we cannot fill it with some triangle or disk by staying on the surface of the donut. And we also have cycles which go round this way, on the, maybe on the top of the donut, on the surface of the donut. And again, there is no way we can fill this in with some disk on the surface of the donut. So here we have actually cycles which are not boundaries. So why am I interested in cycles which are not boundaries? I was actually also interested in forms which are closed but not exact. So we had the vector space of closed, say, J forms, maybe, or K form, maybe K forms, closed K forms. They form a vector space. Well, the sum of two closed forms is again closed. Scaling closed forms makes them closed. Is a vector space. And the exact forms are a vector subspace. And let's call this space Z, maybe with an n on the top. and the subspace B with an N on the top. So B also like, not like exact, but also like boundaries. And we can, in linear algebra, we can form the factor, the quotient space. So this is the usual quotient space. And this quotient space measures actually how far closed forms are exact. If this quotient is a big space, then we have a lot of forms which are closed but not exact. If this quotient is zero, well, quotient 0 means Bn and Zn are just the same space, then yeah, well, this quotient is zero if every closed form is an exact form, and we previously last lecture we actually said there is Poincaré's lemma. Poincaré's lemma, which shows as long as we are on a simplex, I didn't use the word simplex then, so as long as we stay on a simplex or on a cube or on a ball, whatever we want, then actually this quotient is has a name. It is the nth de Rham cohomology. So this is, no, why did I say M? Everything was K. K, everything is K here. K here. This is the case. De Rham. De Rham is a French mathematician. So that is all mathematics, mid-20th century, cohomology. Cohomology. So the case de Rham cohomology, and if we have a manifold which is topologically a simplex, then the case de Rham cohomology is 0. And if we have some space, some manifold where this which is more complicated, for instance, a disk with a hole. So if we have here the disk with a hole, then we have found a form. There is some form which, if we integrate over a cycle here, the integral of this, say, is not 0 but 2 pi, something like this. We have discussed such a form, and it is a one form. And here the first de Rham cohomology, this is a one form. The first de Rham cohomology contains this element, or can be spanned by this element, is one dimensional, and is actually with the basis. We can use this form as a basis of the case de Rham cohomology. So now the cohomology tells us something about topology, and this is why it is so interesting. And even if we do not know the de Rham cohomology, we may still know the dimension of the space. The dimension of the space is also interesting. Is called BK, and has the name Betti number. So the Betti numbers tell us something about the topology of a manifold. So some mathematical results are about Betti numbers, about the sum of all Betti numbers, or some alternating sum of some Betti numbers. This tells us something about the topology. Not everything, but quite a lot. So now, how do these de Rham cohomologies, and why is there a co? Why is it not just why is it homology, and why is it on top of that also a co? I will explain that. So de Rham is just a person, and what makes this co-homology? If we have two cycles, maybe this cycle and this cycle, then we call these homologous, maybe just homolog, I don't know, or homologous, I don't know. If so, this is C1 and this is C2. If no, well, actually homologous, yes. If so C1 is homologous to C2. If C1 minus C2 is equal to 0, and equal to 0 mean, or equivalent to 0, equivalent means this is a boundary. So C1, so minus C2, so minus C2 is this one. And if minus C2 goes this way, then these two cycles form together the boundary of some chain. So actually these two are homologous, or I have to look it up if it is homologous or just homolog. I don't know. And this is homology of cycles. Two cycles can be yeah, well, in the same homology class. So we actually say that the also our vector space of cycles, so that is also a vector space. And in this vector space, there is a subspace, which are the boundaries. And we can, so I call them Z, but with maybe if a dimension K with a K on the bottom. And these I call the boundaries with K on the bottom. They belong here. Is a subspace. And we can also form the quotient space. And this quotient space is the kth homology. Without going too much into details, that is also has also a name. Is called the Čech homology. And Čech was actually a Czech mathematician. So famous Czech mathematician, maybe the most famous Czech mathematician, and his name was Eduard Čech. So his name is Čech. And that looks like something is here connected with each other, and there is in fact some connection through the integral, through integration. So if I integrate over a cycle, so what would be a good name for a cycle? I have already used C for the chains. Maybe gamma, this is a cycle. And a cycle could be, well, k-dimensional. And I have a k-form. K-form, and I want this k-form to be closed. Closed. So a closed form integrated about a closed manifold. So a cycle, something which has no boundary. so a closed form over a closed cycle, then it actually turns out that it depends only on the cohomology class, because if I add here some exact form, then this is actually the same as this plus the integral of this, but this is by our fantastic Stokes theorem, the integral over the boundary, but the boundary is empty. So that does not contribute. So we can add here whatever exact form, or sometimes these exact forms are also called co-boundary. So I can here add an exact form and nothing will change. So this integral actually depends not on phi, but on the cohomology class of phi, cohomology class. So if I form the quotient space, then all these elements of the quotient space are actually equivalence classes. I can add anything, any exact form, which is what I factor out in my quotient space, and that gives me the cohomology class of phi, and this integral over a cycle only depends on the cohomology class. But also, if I have here a cycle plus something which is a boundary, maybe capital gamma. So if I add here just the boundary, and also multiply apply this integral on k form. So it's again a k form and again closed. Then this is actually the integral of gamma as before, plus the integral. So by the way, when we integrate a linear combination of chains, this just means we integrate over all of these chains separately and scale the integral by the scaling factor in front of the corresponding chain. So d gamma phi, but this then is, so this is integral of phi gamma plus that is in fact the integral over gamma of d phi, but now d phi is equal to 0 because we assumed that this is closed. So this does not contribute, and this means that our integral depends only on the homology class of the cycle. Therefore, our integral actually is some mapping from the de Rham cohomology of our manifold and the Čech homology into the real numbers. So we have actually this, it's linear in both, it's a bilinear mapping, which takes a representative from a cohomology class, which is a closed form. Exact forms are not interesting, so hopefully interestingly, a closed form, if such a thing exists, a closed non-exact form, and we integrate it over, well, if it exists, over a cycle which is not a boundary, because if it was a boundary, it would not be interesting, we would get 0. So now this well, in mathematics we call such a thing. This is a vector space, and this is also a vector space, and such a bilinear mapping with two vector spaces which takes real values or whatever our um, field. Actually, this is also interesting with the rationals. So very often this is considered over the vector space of with a field being rational numbers. So that is also an option. Such a mapping is called a pairing. And now, well, it is quite interesting. So this pairing may be non-degenerate. Non-degenerate. What does not non-degenerate means? So I have a vector space V and a vector space W. If for any x in V, x is not equal to 0, there exists a y in W that this pairing, well, say integral over, say, maybe a y of x is different from 0. So there is no form, well, for every form which we have, which is not 0, for any closed but non-exact form which is not 0, we actually find some cycle for which the integral is not 0. So that would mean non-degeneracy. So non-degeneracy, and the other way around. So for any y in this, for any cycle which is not a boundary, we can find a form which is closed. So that also the pairing, the integral is different from 0. So in this case, we call this non-degenerate. It's actually just linear algebra. It's a linear algebra thing. A pairing between two vector spaces are non-degenerate if we can we have this bilinear mapping. So that is actually the bilinear mapping, linear and x, linear and y. So that bilinear mapping, if that is non-degenerate, then actually it turns out that both spaces are isomorphic to each other. So more precisely, they are isomorphic to its dual, but we know that the dual space to a finite dimensional vector space is isomorphic to the original vector space. So in particular, they have the same dimension. If we have such a pairing which is non-degenerate, then we actually know we have, roughly speaking, as many closed forms which are not exact as we have cycles which are not boundaries. So cycles which are not boundaries is geometry. That is something we can visualize, which well, we can take our donuts with handles or whatever, and we actually see what the cycles they are, or what the non-boundary cycles are, which is much easier than coming up with, well, what actually are the one forms which are closed and not exact. But we know there are exactly as many in terms of a vector space as we have these nice geometric objects, cycles which are not boundaries on a donut. So now I put this non-degenerate in quotes, quotation marks. That is something which needs to be proved. And if we have such effect that we have, well, some kind of homology space and some kind of cohomology space, and of course we can pair them, and this pairing turns out to be non-degenerate, we call this Poincaré duality. Poincare. This is called Poincare duality. If we have this, and Poincare duality is a very good thing. If we have Poincare duality, then we can establish that basically knowing the cohomologies, de Rham cohomologies, which is a calculus thing. That is a calculus thing. We get some information about the geometry, the topology of the manifold, which is a geometric thing, which is topology. So two completely different things, seemingly unrelated, have that very deep relationship. So in our university, our colleague Bea Bleile works on Poincare duality. So if you get on a talk with her, most likely it will involve some kind of Poincare duality. So that is Poincare duality on manifolds, where it is actually established on a manifold. We have Poincare duality, and we can. But by the way, also physicists are very much interested in the topology of some time space or some physical spaces. And we see here that if we have such topological problems or interesting features of our manifold, then also analytically things can go wrong in terms of say a field which looks like being having a potential, being conservative, but then has no potential because something goes wrong with the topology. Now you can take two different points of view. You can find it a bother. You can find it interesting. So probably it's interesting. That is quite interesting. So I think with Poincare duality and cohomologies, de Rham more precisely, de Rham cohomologies and Čech homologies, I will conclude this course with 12 double lectures. This is quite a lot of material. Next trimester will be very busy, and I have committed to a unit on theoretical mechanics or mathematical methods of theoretical mechanics, for which there exists some very old recordings. I'm not sure if I have time to do some new recordings on that. Maybe not sure yet. What I do at some stage, I would also like to continue this. There is one topic which at the beginning I thought would be interesting and relevant to mathematical physics. This is Lie groups, Lie algebras, and representations. I didn't get to this. This would be something where one could continue here. Also, we did not get very much into Riemannian geometry when we have on our manifold at each tangent space metric inner product, which changes a nice tensor. So that would be something to continue. So lots of things to get that could possibly be done in maybe second and third trimester. In second trimester, I teach only one undergraduate. Only one undergraduate unit, so maybe it will be easier then. So it is not the whole 1.5 hour today, or is no, actually it is. It's not 2 hours, but it's 1.5 hour, which is quite a lot to listen to. It's much harder to listen than to. So have you any questions right now? So I think that is a good conclusion for the
I don't have a question about the content, just about the lecture notes. It appears we've gone slightly, actually a fair way beyond the most recent iteration of the lecture notes, which is good, I think. Are there any exercises to go along with the more recent material, or?
I will think about that. Of course, to well have an assessment of the whole unit, it would make sense to have also some kind of assessments. Maybe I will. Well, it could be as so I think I have alluded to that, but something well finding the cohomology on some donut or this well probably something like this when it comes to these last topics here, and well maybe something like this. So it would be good to have some problems which also reinforce your understanding, to get your hands in it. So maybe should come up with some problems. Yeah.
Beauty, thank you.
Good. Oh, okay. Then so how does it work? I need my control back. Here it is. And there was something in the chat which I made. Two cycles are considered homologous. That is the word, is it? Well, yeah, homologous.
So there's
Uh,
these subjects. I'm gonna study it more in depth during trimester 2. Which type of assessment we will get for it?
in which in this subject here.
Yeah.
Well, I said well some of the problems from the lecture notes, but the lecture notes do not cover the last topics here, so I need to add something there. And well, all or not. I had actually with Weir, who is not here today. Maybe I can actually stop the recording. This is what I wanted to do. Stop recording. Yeah.